In this video, we're going to review properties of polynomials, and we're going to look at what their leading coefficients and degrees tell us about what their end behavior looks like, as well as we're going to use properties such as the zeros of a polynomial to both write possible equations and also sketch graphs. Recall a polynomial is a expression that's really nice. They're like the common building block things that we see. They're made up of monomials added together, monomials of unknowns or variables that are to positive or zero, positive exponents or the zero exponent. And they're not only positive, but they're positive whole number exponents. So they're the nice things. They're like x squareds and x to the fourth powers and so on and so forth. Polynomials are really nice because they have some really nice properties, like they're continuous. Functions that are continuous, you can graph by putting your pencil in the paper and then drawing the graph without ever having to pick it up. Meaning there's no breaks in the function, there's no holes, there's no gaps, there's no jumps, there's nothing fancy or crazy going on. And also they're smooth as well. They don't do like jagged, sharp edges or things like that. They're smooth along the way, which also grants them really nice properties to do further calculations with. Because of that, we want to think of what happens when the inputs get really, really large, really, really positive, or really, really negative, because polynomials can take in any x value on the real line. And you may recall from Algebra 2 studying this a little bit. In particular, we would like to know what happens with even degree polynomials like parabolas, like I've got a sketch here, or maybe they're other even degrees, maybe they're x to the fourth or x to the sixth or things like that. They all have the same basic shape. They might wiggle a little bit in the middle, but in the end, they all kind of more or less look like a U shape if you zoom out far enough. If the leading coefficient is positive, they open up, so you get something. So you get something more or less, maybe some wiggly in the middle, that looks something like this, where as x, the inputs tend to infinity, the outputs also tend to infinity, and as the inputs tend to minus infinity, the inputs still tend to positive infinity, meaning they go up on both directions. If the leading coefficient is negative, it's the same thing but upside down. So as x tends to positive infinity, the outputs tend to minus infinity. And as the inputs tend to minus infinity, the outputs still tend to minus infinity. The outputs, no matter what the input's doing, the outputs behave in the same way. Odd degree functions do not behave that way. Odd degree functions think of some odd degree functions like the line y equals x, or a cubic. Odd degree functions go in opposite directions. So one's goes up and one's goes down. So maybe a graph of a cubic, if the leading coefficient is positive, you get a graph that looks something like your standard cubic, where as x goes farther to the right, the function gets further up. Or as x tends to infinity, f of x, the outputs tend to positive infinity. And the reverse is true. If we go to the left, and we tend to go down. And vice versa. If the leading coefficient is negative, then the behavior flip-flops. You get something like this. Again, when x goes to positive infinity, now the function's outputs go down. And when we go to the left, the outputs go up. This long-term or end behavior is something you should be able to identify based on the polynomial. So here's a few polynomials, and we'll deduce these things. What is the leading coefficient, the degree, and determine the end behavior. For this first polynomial, I think the leading coefficient, leaders are in front. It's the coefficient in front of the the greatest degree term, and that's -3. The degree is 5. So it's an odd function with negative leading coefficient. So what's the end behavior? As x tends to positive infinity, the output, well, this is a negative leading coefficient of odd degree. That's like this guy that tends to minus infinity. And as x tends to minus infinity, the output tends to positive infinity. Again, to sketch this thing looks something sort of like this. In this case, the leading coefficient is 5. The degree is 4. So this is a positive leading coefficient of an even degree function. That's like this guy. It means this looks something like this, like a W of some sort. So therefore I know that as x tends to infinity, as x goes to the right, the function goes up. And as x tends to the left, the function also goes up to infinity. Lastly, what's the leading coefficient here? That's what I get if I distributed this 3/4 everything. It's 3/4. The degree is 5. So this is odd degree of positive leading coefficient. So that's, again, has to look something like this. As x tends to infinity, f of x also tends to infinity, and as x tends to minus infinity, the output tends to minus infinity as well, tends to go down.